Good morning, friends. Today we are going to discuss parallel resonance condition. The parallel resonance condition in AC circuit, the circuit diagram for this condition is given here. In this circuit, we can see that an inductor of L Henry having some resistance R is connected in series, and this whole combination is connected in parallel with a capacitor of capacitance C. Okay, so as we know that in series resonance, when the voltage is in phase with the current, then we will say that the resonance is achieved. So in parallel resonance, the same condition is achieved. Okay, now you can see that in if the V is the supply voltage here, this is the V supply voltage, sinusoidal supply voltage, and IL is the current flowing into the combination of resistance and inductance. This is the IL. Okay, this whole combination is ZL. Okay, ZL equals to R plus J XL. So as we know that in case of inductance, the current IL will be lagging by the supply voltage V by some angle omega L. IC is the current flowing through the capacitor, and it is leading supply voltage V by exactly 90 degree. So if we take out the component of IL, we have two components, IR, which is IL cos phi L, and second component is IL sin omega L. So under this condition, the circuit current IR, will only be in phase with the supply voltage when IC equals to IL sin phi. ओके, जब ये कंडीशन मीट आउट होगी तभी मैं बोलूंगा कि जो सर्किट करंट IR है वो सप्लाई वोल्टेज V के फेज में होगी. ओके, सो moving further, what we were doing in earlier, we are doing in series when we are changing the frequency. Okay, so we are changing the frequency or we are increasing the frequency. Okay, and subsequently we'll see the changes in the network conditions or parameters. Okay, so what we can see in parallel resonance condition, we have already seen that IC equals to IL sin phi. Okay, so if you want to make an impedance triangle here, this is phi L, this would be R. Okay, and this would be, I would say, this will be for example, if we want to write like so first we have to solve this. So that IL will be nothing but V divided by ZL. And what is ZL? ZL equals to R plus J XL. Okay, if we want to write IC, that IC will be nothing but V divided by XC, which is the capacitive reactance. XC is the capacitive reactance. And if you want to find out sin phi L, that sin phi L will be XL by ZL. So how it came from? Okay, so if we make an impedance triangle, now come here, this is R, this will be XL, and this will be ZL. So by this relation of impedance triangle, we can write sin phi L equals to XL by ZL. Simply put the value. If we put the value of these parameters in IC equals to IL sin phi L, what we get? Let's put this value. So IC will be V by XC, right? Okay, then IL will be V by ZL into sin phi L. The sin phi L is XL into ZL. Okay, so that V can be cancelled out, and simply we can write here that the XL into XC is coming to be ZL square. Okay, that XL is omega L and X equals to 1 upon omega C, so that we can simply write equals to XL square or sorry ZL square, and that ZL is nothing but R square plus XL square. You know that because I have already written ZL equals to R plus JXL. So ZL square will be R square plus XL square. Okay, what we can simply write? Now we can write L by C equals to R square plus that XL equals to omega L square. And once we solve it, and if you want to take that condition that omega, you know that omega is 2 pi f, and if you are considering the resonance condition that f will be fr, so omega equals to 2 pi fr, and if we solve this overall condition, we'll get that fr comes to be 1 upon 2 pi under root of 1 upon LC minus R square by L square. So this is the condition, or this is the resonating frequency under parallel resonance condition. And if R is very less, we'll get the same condition as we have obtained in series resonance, that FR will be 1 upon 2 pi under root L into C. So in series resonance, what we were amplifying the voltage, but in case of parallel resonance, we are amplifying the current. So if you want to compare the series and parallel resonance circuit, we can simply write that in series we can make two column. Okay, we can make two column. And what are the first? Impedance. In impedance, in case of series circuit, we can simply write that in series circuit that impedance is very low, that was simply R. In parallel resonance, it is maximum, that ZR, I would write ZRP, that impedance under parallel resonance condition, it will be L by CR. Okay, L by CR, and it is totally, you can see that L by CR, there is no frequency term is associated, L, C and R, so it will be resistive only, and that ZRP, the unit of ZRP will be ohms. Okay, but what we say, in series resonance condition ZR was very less, but in parallel resonance ZRP will be very high. So since impedance is very in series resonance impedance is very less, so current is maximum, but in case of parallel resonance that RP is very high, the impedance is very high, definitely the current will be less. What I would say, that in series resonance current will be maximum, but in parallel resonance current will be minimum. Now third is resonating frequency, that FR. So in FR it is 1 upon 2 pi root LC, but if you write parallel resonating frequency, you have to write the overall condition, which is 1 upon 2 pi under root of 1 upon LC minus R square by L square. Okay, that's the generalized expression. One more thing which has to be known, that power factor. So you know that in since the voltage phasor is in phase with the current phasor, so power factor will be unity in both case. In both case. Okay. Now fifth, basically in series resonance country it magnifies the voltage, but the parallel resonance country, the parallel resonating circuit basically amplifies the current. So voltage amplification takes place, and in parallel resonating circuit current amplification takes. So basically amplification. Okay, so we have seen all the factors associated with the parallel resonating circuit. One more thing which I'll be going to explain is the quality factor associated with the series and parallel. So that will be covered in the next video. Thank you very much.